Hi, my name is Datis, and today we'll be going over indirect descriptors. We'll also be covering some information on vowel block. Now, I hope you started this MP because you might be noticing that some of the applications you have used for VertIO might be a bit different for vowel block. Furthermore, if you've watched a previous video on VertIO, you'll know that what we're going to be covering for indirect descriptors is just an extension of what was covered previously. In this video, we're going to go over some background information on vowel block. We're going to also cover obviously indirect descriptors, where they're extremely helpful, and then a visual example. So with that ado, let's get straight into it. Now, VertIO uses descriptors to specify operations, and we know this. In your VirRNG device, you used a descriptor. You used the address field to specify where the buffer lived, the length flag to specify the length of that buffer, flags for what to do with that buffer, and then the next field, which we didn't really cover fully, and we will in this video. Now, I want you to just leave you with this idea that we're going to touch very soon in this video, but remember that descriptors are not just meant for buffers. Remember that with the address field, they can kind of point to anything, and this length field just has to specify the length of what it's pointing to. Just keep that in mind when we cover the rest of this video. In your VirRNG device, you used a descriptor to specify where the buffer lived, the length of that buffer, and what you wanted to do with that buffer. Now imagine if you had a device that required multiple descriptors in order to work properly. We're talking networking drivers, video card drivers, drivers to send data to a microcontroller, and the most important of all, the vowel block or the storage device for your MP. Now, these devices all need more than one descriptor to detail modes of operation due to increased complexity of the information or processing that needs to happen. Now, I want to expand on the storage device because that's what you're going to be covering for your MP. A storage device, especially of that of a hard drive, needs a few bits of information before it can do anything with a provided buffer in the operating system or your computer's memory. Namely, for example, a hard drive will typically break up its storage that it has. Let's say that in our example we have 16 megabytes of total storage in our hard drive into chunk level partitions. These partitions are also the sizes of what each block of data that can be sent and received between the storage device. Okay, that was a whole bunch of word vomit. What does this mean? Well, what I just mentioned is called block addressable storage, meaning that you can't just ask your hard drive to send you individual bytes every single time you make a request. It's going to spit a fixed size chunk at you, and you can only spit fixed size chunks at it, the storage device. So keep that in mind for the buffer lengths. Because of this, a storage device will typically ask for what's called a sector before it modifies or reads anything from the provided buffer. That specification for what sector that the storage device needs to spin to or get to, that's already one descriptor. Remember that the address field can only specify one location in memory, and the flags will determine what that device or a hard drive can do with that specified location in memory. So I want you to think to yourself, if the descriptor can specify only one memory location at a time, and we need to tell the device beforehand what sector to spin its arm to for the device that we are, for the data that we're looking for, why might we need multiple descriptors for that? Well, I'll give you a bit of the answer. It's because we need some kind of data structure to tell the device that. And we also, hint, we need to tell the device what mode of operation that it needs to be operating in, whether it needs going to be reading or writing. So you might be needing other descriptors to specify other data structures so that your device will function properly. More information on what I'm talking about is going to be found in section 5.2. I gave you a bunch of hints. You need to find what kind of data structure will tell you the sector, or in this case, where the storage device needs to go to. But remember, the point that I'm trying to drive home is that you can't just use one descriptor to do all these things. If there is one data structure that you want the device to only read from, to just prime itself to work properly, that will be read only. But because your hard drive needs to do read and write operations, having one entire data structure that you will just only read from just won't work. So you need multiple descriptors in order to have one location where the device can get preliminary information to set itself up, and then another descriptor to handle whatever needs to happen. Again, more information is on section 5.2 of the OASIS documentation. So hopefully that's enough of a start to kind of get you, working on the vowel block. So all of this leads to some pretty complex logic if you're implementing all of this wraparound logic that we were discussing in the previous video. So, what if we didn't have very many spots in our avail ring or other locations in our descriptor table? In comes indirect descriptors. Now, the idea is that with one descriptor in our descriptor table, we can essentially tell our hard drive to look somewhere else in memory to complete the request rather than having to constantly look at the avail and descriptor indexes to fulfill the operations that we requested as the operating system. So rather than this, we can have something like this. So I know you're already wondering, how do you even do this? And what does this look visually? And I'll walk through an example here. Okay, so for this example, we're going to cover what an indirect descriptor is doing visually. So here we have our avail ring. So let me just switch to, we have our avail ring here, and we only have one descriptor in our descriptor table. Note, this lone descriptor for the topic of indirect descriptors is our indirect descriptor. So what an indirect descriptor does is that it sits in our actual descriptor table, and all it will do is that it will just point to another location in memory that you will specify in the same setup process that you do. So your ADDR will essentially just point to another table, or so in this case, typically it'll be a starting point of an array of other descriptors. So we'll have the same idea. So this 1, 2, 3, 4, 5. And then we have length, flags. Next. Now let's say that for this example, our indirect descriptor is pointing to an array of 5 other descriptors. Remember, the thing that this indirect descriptor will be pointing to will be a location of other descriptors that will be stored in an array. For this example, we will use 5 other descriptors, but in no way is this the exact amount of descriptors you will use for your vowel block. That'll be up to you to figure out. But in this case, hypothetical example, we have 5. So we have desk 0, and let's say that this points to AF00. Make this a bit neater. And let's say the length of the thing that it's pointing to is 32 bytes. The flags will be just to read from it, and the next will be 1. So I promised you that I was going to talk about what this next thing is. But before I get into that, let me circle back to what's going on with our sort of lone descriptor that's sitting on our descriptor table that's specifying where these other descriptors live. So remember that this descriptor sitting in your descriptor table here is pointing to other descriptors in memory that are not being kept track of by your avail or used index. So what's going to happen is, because this descriptor is pointing to a set of other descriptors that your device is going to look at, the length of this will be the number of, let's say, the number of descriptors that you're sort of pointing to times the size of the struct of the descriptor. So if you have 5 descriptors that you're pointing to in another place in memory, then it'll be 5 times the size of that struct. For flags, it's going to be indirect, or wherever you can find that, because we're essentially wanting to tell the hardware to look somewhere else in memory, right? So it's going to be, your hard drive will basically look at your descriptor and basically say, okay, this is where our main set of other descriptors live. Here's the size of what I'm going to be dealing with. Oh, okay, so this descriptor living in our main descriptor table doesn't actually tell us anything to do with like data buffers or stuff like that. It's telling us to go look somewhere else. Now, there's this mysterious next. And what next is telling the device is after the device sees that it's dealing with an indirect descriptor, it's no longer going to just look at your descriptor table for other descriptors to fill out buffer data or read from buffer data. It's going to look at the address that you provided. So that saves you a lot of math overhead from you having to modify this avail, because rather than having like, you have a ring, sorry about the ring 1, and this is pointing to 1 or whatever. Now, and then you have to have multiple descriptors, and then you have to make sure that your use follows a whole bunch of other stuff. It saves you the headache, or reduces the amount of headache of the sort of wraparound logic that you have to do with the topics that we discussed in the previous video, where you have to have a modulus check where, does your descriptors wrap around the size that you gave it. So for these descriptors that are now referenced in this other part of memory, what this next pointer basically says, not the next pointer, but this next flag here says, is that, okay, now I've just finished looking at this descriptor, where do I go? And it basically says 1, pointing to this descriptor here, descriptor 1. Let's say this is a bunch of other information. It's basically telling the device to offset itself 1 more from where it currently is to look at the next item or next descriptor that then is going to specify other details. So if we imagine this set of other descriptors that are being pointed at, sorry, that's a terrible drawing, as basically an array. You have desk 1, desk 2, so on and so forth. It's the descriptors, the next flag essentially just says where should you, descriptor 0, descriptor 1, descriptor 2. Sorry about that error. So what this next flag is saying is, hey device, you're at 0, you're at the starting position. Where should you go from here? Okay, go an offset of 1 of this struct type, which will then increment it to the next descriptor within your table. Or in this case, typically this will be stored in an array. So then say this descriptor will be ff0, let's say the struct or data structure that the address is pointing to is 64 bytes arbitrarily. The flags are to write to it, and the next will be 2, which will then just be the next thing in this table or array. These are all just random addresses, by the way. So you get the point. Now for our last descriptor, the next will basically just be 0, because this is to signify to the device that you've reached the end and there's nothing for you to look here. There's nothing for you to sort of look. So this is how your hard drive will know that it's reached the end and no longer has to keep going past the array, because the offset from the last item or the last descriptor will be 0. And so that'll be the end. And also you gave it the length in your actual main descriptors in your descriptor table of the amount of descriptors there are that you're basically telling to process elsewhere. So the thing that I want to drive in home is, rather than you having a whole bunch of other ring 0, ring 1, and having a whole bunch of stuff in your descriptor table, which you would then have to keep track of how many descriptors you have and increment your, have a do your modulus check to ensure, okay, what do you overwrite? You essentially just have, in our case, in the simplified example, one descriptor, and then points to somewhere else. Device processes that, and then just pretends as if it just processed this descriptor alone. In the sense that our IDX only increments by one, and then wherever the used IDX is also only increments by one. So I hope this example kind of helped to kind of showing what indirect descriptors are doing. The whole point is just to reduce the amount of descriptors we have in our main descriptor table. And alongside the other reasons mentioned, it's just also going to reduce headache when you have devices that require more than one descriptor. Of course, you're free to do whatever you'd like. You're free to choose whatever implementation you want. But other than that, I really hope you guys have found this video helpful. And hopefully when the next set of content comes in for MP3 that you guys find that helpful as well. Good luck on the rest of your MP, and hope to see you guys again soon.